Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, today is the last lesson of chapter 3. Once again, you get some of these lessons that don't necessarily fit into some other chapters, tuck it into the back of one of a chapter, so learning about the properties actually does fit in pretty well with what we're doing in this chapter. The two specific properties we're going to work with are commutative property and associative property. And my goal is to not have you memorize what these properties are, but to understand why it's so helpful to understand that these properties exist and you can actually do these things with these numbers to make your life easier, basically. So starting with commutative property, you've probably heard that once before, maybe didn't remember exactly what it meant, but the commutative property says that you can rearrange the order of the numbers that are being added or multiplied and still get the same answer. So consider this problem here. If you used order of operations, you would take 27 and add it to negative 175. And then once you found that sum, which would definitely be negative, right? Somewhere in the negative 140 some, 50 some range, then you would add that number to 173. But I'm thinking, okay, let's try this. What if we rearrange the order? See, I noticed something about the 27 and the 173. If you were to add those numbers together first, rearrange the order, and now go from left to right, the sum of these two numbers is 200. And now we can solve this mentally, because you know that to count up from 175 to 200, that's a difference of 25. And so a lot of times, if you can find some pairings of numbers that you can solve mentally, then it's going to be a lot easier to solve the problem rather than going from left to right and doing all of the work. Okay, so that's commutative property, being able to rearrange the order of any numbers that are being added or multiplied. It's legal to do that, and a lot of times you'll see something like this. 1 plus 2 plus 3, we know is equal to 6, right? Well, let's reverse the order of the 3 and the 2. What is 1 plus 3 plus 2? It's still 4, 5, 6. So that's another example of commutative property. For associative property, typically when we see associative property, this is the one where you don't change the order of any of the numbers, you just change how they're grouped. So you move where the parentheses are. So associative property says that it doesn't matter how you group numbers when adding or multiplying, the answer is going to be the same. So once again, you look at this, and if I'm going to multiply negative 41 times 25, figure out that answer, then multiply it times 4, that's going to be a little complicated. But what if you decided, hey, let's not give priority to this section, let's give priority to that section instead and multiply 25 times 4. 25 times 4 is 100, and now multiplying negative 41 times 100 is easy. Your answer is going to end up being negative 4,100, and I didn't have to show any work. I didn't have to do any calculations on a calculator. I was able to do it all mentally simply by using associative property. Okay, so once again, let me give you a simple example here. 1 plus 2 plus 3. If I add these two together first, I get 3 plus 3 is 6. But if I decide to take 1 and then add it to the 2 plus 3, 2 plus 3 is 5, and then 5 plus 1 also gives us 6. So associative property is about keeping the order the same, but moving where the parentheses are, changing the groupings so that it changes which ones you add together first. Whereas commutative, just rearranging the order of things so that it makes it easier to add or multiply. Okay, so remember when operations with numbers were simple? In elementary school, you learn to add, subtract, multiply, and divide whole numbers. As you have seen, there is a lot to consider when operating with different kinds of numbers. In this lesson, you will put together much of your understanding of operations with integers and simplifying numerical expressions to draw conclusions about order and grouping of operations. All right, so let's copy this down. Juno was working on simplifying this expression, 24 plus 3 plus -4 plus 7. I know, he exclaimed. It must be 30 because 20 plus 10 is 30. And you're like, 20 plus 10, what are you talking about? There's no 20s or 10s in there. So is he correct? Is this value 30? Well, we can check it, right? Let's go ahead and go from left to right. What is 24 plus 3? That's 27. And 27 plus -4 is equal to 23. And then 23 plus 7 is going to give you, yeah, that's definitely going to give you your 30. So he was right. So where on earth did he figure out where the 20 and the 10 are? Have any ideas by looking at that? How could Juno have found 20 and 10 in this expression? Well, by using commutative property, he's able to rearrange the order of the numbers. So the 24 and the -4 combined to make 20, right? If you just rearranged the 3 and the -4 and then decided to do this section first and then that section next, you get your 20 from the 24 and the -4 and the 10 from the 3 and the 7, and 20 and 10 are easy to add mentally. So here's Juno taking advantage of understanding these properties, this time specifically commutative property, to rearrange those orders to put the ones together that go together nicely and solve the problem in his head. So in problem 112, Juno used the understanding of two different properties, commutative property of addition and associative property of addition. We've already talked about this in detail, so let's scroll down here, talk with your team about commutative property of addition. Okay, so I just want you to think. I already sort of gave you a hint when we were opening up this lesson. Does it work for other operations? Does it work for multiplication, division, and subtraction as well as addition? And the answer to that is, well, it works for addition and multiplication, but it doesn't work for addition or for subtraction and division. Okay, so once again, here are some examples of commutative property where you're rearranging the order of numbers being added together and you always get the same sum. When you rearrange the order of numbers being multiplied together, you get the same product. So commutative property applies for both addition and multiplication. Okay, then consider associative property. Does this work with other operations? And the answer is, well, yes, but only addition and multiplication again. Change the grouping here. 4 plus 3 is 7, and 7 plus 6 is 13. But what if we decided to add the 3 and the 6 together first? Then it would be 4 plus 9, which is also 13. Okay, 10 times 9 is 90, or 2 times 45 gives you 90. It works for both addition and multiplication, but not subtraction and division. And I think we're going to get into that a little bit, explore a little bit more. Okay, so consider each of the following, consider expressions involving addition and subtraction, such as 7 minus 2 plus 4. Can you tell me what that's equal to? Just go from left to right. 7 minus 2 is 5, and what's 5 plus 4? It's equal to, wait, what did I do? Oh, dadgummit. Hold on. Let me work some magic here. That's better. That's a 4 there, not a 5. So 7 minus 2 is 5, so 5 plus 4 is 10. So just by using order of operations, all you have left are the addition and subtraction, so you go from left to right. Okay? So does grouping matter? In other words, would 7 minus 2 plus 4 give you the same answer as 7 minus 2 plus 4? Remember, the parentheses tell you to give priority to whatever's inside the parentheses. Well, this is still going to be 5 plus 4. What's this one going to be? That's going to end up being 7 minus 6, which is 1. So the grouping does matter. Okay, so the answer to this question, does it matter? Yes, it matters, meaning that you get a different answer. So if we're going to group this properly to get the same answer that we got here, we would have to put the parentheses around the 7 minus 2. And if you wanted to change your priority and add the 2 and the 4 together first, the fact that you're subtracting here is going to make a difference, right? Because that's supposed to be a -2, right? But if you put parentheses around the 2 plus 4, then you're changing it to a positive 2, and then eventually the total sum ends up becoming a negative 6, right? Because 7 minus 6. Now, does the order matter? If you were to just rearrange the order and not do anything with the symbols, will that make a different answer? And the answer to that is yes, the order matters too. When you are subtracting, commutative property doesn't work. 7 minus 2 plus 4 is 5. But if you switch the 2 and the 7, see, the minus sign is attached to the 2, which means it's supposed to be a negative 2. But when you rearrange the numbers without also changing that sign, now you're making the 7 a negative when it was supposed to be a positive. Did I say that right? You're making the 7 a negative when it's supposed to be a positive, and you're making the 2 a positive when it's supposed to be a negative. So this does not work for subtraction. So find the expressions that involve addition and subtraction. In what order would those operations be calculated? What does PEMDAS tell us to do? We're supposed to go from left to right. Okay, so let's go ahead and use order of operations, use the left to right rule to simplify each one of these expressions. Okay, pause, copy these down, and then work from left to right. And then when you're ready, unpause and check to see that you got the same answers that I have. Which time are we working at? Okay, this looks good. All right, so 10 minus 2 plus 4, you would do the 10 minus 2 first because they're the first two in this problem, in this expression. So it's 8, and then 8 plus 4 gives you an answer of 12. Here you have to go from left to right, so you're going to get 3 minus 5 is negative 2, and negative 2 minus 2 is the same as negative 2 plus a negative 2, which is negative 4, and then negative 4 plus 6 gives you 2 for an answer. And then the last example, 7 minus 3 is 4, and 4 minus 2 gives you positive 2 for your final answer. Okay, so it would be interesting if we couldn't rearrange those, so we would have to do something to these expressions in order to use commutative property and rearrange the order of those numbers, which we'll get to. All right, so Juno has another idea. He says, wait, can't subtraction be rewritten using addition? Since order doesn't matter when we add, we can just, can't we just rewrite the subtraction as addition so we can use any order? And so, yeah, in this situation, he's exactly right because we have the luxury of using KFC. And when we do KFC, we can change the subtraction problem to an addition problem. So this would become 17 plus a negative 4. And then that negative 4 plus a negative 11. And then that negative 11 gets the key. You just keep it as plus 15. So once you've got that rewritten as an addition problem completely straight across, then you're allowed to use commutative property and rearrange the orders. Okay, so go ahead and see if you can rewrite these expressions, and this one probably is going to be a little tricky. Don't worry, show your work. It's okay to make mistakes. We can correct them and get it right. But I would rather you try and get it right on your own and make a mistake than just wait and copy me. Okay, so give it a shot. Unpause when you're ready. All right, welcome back. So you see how I've rewritten this using the KFC. So instead of minus 4, it's plus a negative 4. Instead of minus 11, it's plus a negative 11, and then plus a 15. So in this case, I'm thinking add those together first. Then once you've got that, then that combines nicely with the 15, and all we have, those are the forms of zero pair, right? Negative 15 plus positive 15. So your answer is going to end up being 17, which is much easier doing it that way than it would have been just going from left to right. And here, what do we have? Negative 2 plus a negative 2 times 3 plus negative 4 plus negative 2 times negative 4. Now, we do have to do multiplication first. That's critical. So the negative 2 plus 2, we can't add those together to make 0. We must give priority to the multiplication here. So that's how it becomes negative 6. And here, same thing. We must give priority to the multiplication before we do any adding. So -2 and -4 make +8. So now let's group them together. Let's put the 2 and the 8 together to make 10, and the -6 and the -4 together to make -10. And when you add those together, you end up getting 0 for an answer. Okay? Go ahead and pause this if you totally messed up on either one of those and you want to erase or cross out and redo it. Maybe I'll remove some of my color coding there so it doesn't confuse you. Or maybe you like the color coding, so just pause it before I remove those guys. And then have at it. All right, so I'm moving on. You pause if you need to take a little more time. All right, Maria and Jorge were trying to simplify this expression. Now that looks like a mess, right? -4/3 times 1 2/5 times -3/4. Maria started by going and saying, well, let's change the 1 2/5 to an improper fraction. And then when we multiply, we can, what did she do? She decided to multiply these guys together first and then multiply everything. And what was there? 2 different negative factors. So the negative times the negative turned the eventual answer into a positive. Then she changed it back into a mixed number and then simplified the fraction part to get an answer of 1 2/5, which is interesting because looky right there. What does that tell you about these two fractions? So really, take a look at those two fractions. What would you call the relationship between those two fractions? They are what you call reciprocals, right? And when you have reciprocals and you multiply reciprocals times each other, they always equal 1. Right? So you take 1/2 times 2/1, you get 2/2, which is equal to 1. If you take 4/7 and you multiply it times 7/4, you are going to get 28/28, which is equal to 1. So here, Jorge noticed that these two multiply together to make 1, and then 1 times anything is going to equal that number. So, yeah, that works just fine. You can do the hard work that Maria did, or you can do the easier work that Jorge noticed. So this is one of the reasons why, we want you to have a deep understanding of how this math works, because once you understand how the math works, you don't necessarily have to memorize processes. It just makes sense. You just follow the logical process, okay? So Jorge used the commutative property of multiplication. Why might Jorge have decided to multiply these together? Because they're reciprocals. They end up equaling 1, right? So in a multiplication problem, the factors can be grouped together in different ways. This is called associative property of multiplication. So we have commutative property of addition and commutative property of multiplication. We've got associative property of addition and associative property of multiplication, which they basically say the same thing. You're just changing your operation. That's all. Okay. So what do I have over here? Let me just check what's going on. Okay. So use this property and show that 3/4 times 2/5 times -2 and 3/4 times the product of 2/5 and -2 will be equivalent to each other. Okay, so here when you multiply 3/4 times 2/5, you're going to get 6/20, right? So 6/20 times -2/1 gives you -12/20, which simplifies down to -3/5. If instead you chose to multiply, maybe I'll get out of there. Maybe I'll just get rid of this guy. The 2/5 times the -2 first, and it becomes 2/5 times -2/1, which is -4/5. You multiply straight across, you get -12 on the top, 20 on the bottom. Same thing here, same exact answer. Okay, so this absolutely works for multiplication. So copy down those 3 problems and choose to use any property that you like, whatever seems to make sense for you. Simplify those expressions. Hopefully you'll be able to do it mentally without too much trouble at all. Okay, go ahead and give that a shot. I'll pause for a second. All right, are you ready for the big reveal? I think this one is one where you just go from left to right honestly, I think multiplying -9 times 1/9 to give you -1, and then anytime you multiply -1 times a number, it's just its opposite. So our answer there ends up being -3/8. What do we want to do here? This is a little tricky. Notice how if you multiply 3 times 4, you get 12 in the numerator here, and then you can do some cross-canceling. Remember how that works when you're kind of simplifying fractions before you multiply straight across? So now you're left with -5 in the numerator of this fraction and 63 in the denominator of this fraction. So they combine to give you the final answer of -5/63. And then here, what's 5 times 2? It's 10, right? So let's do that first. And then anything times 10, you just move the decimal one place to the right. So you end up with an answer of -81. All right. Here we go. Problem number 118. Please read through all of these problems. This is like the culminating kind of word problems where we're just going to use basic math, okay? 5 different word problems that are probably, if I recall, are either going to be multiplication or division problems involving rational numbers. So read through, see if you can figure out how to get to the answers, and then I will do the review, but take your time on this. You don't necessarily have to. What happened here? What are you doing? Stop it. I don't want that at all. Why you do this? Get out of there. Sorry, I'm going to pause and get back to where I was before. Okay, I'm back. Sorry, must have hit a button by accident. Okay, so when you're doing word problems, students ask me this all the time. I don't want you copying down the entire word problem. If it was a problem like what we had here, where you had to copy down this, yeah, copy down the number part. But with the word problems, you copy down the essential information, which are the numbers, and then you determine what operation you need to do, and then solve it. Now, when we get to chapter 5, I'm going to teach you something that's called the 5D process. And we are going to spend the chapter basically analyzing word problems, and we're going to integrate some algebraic reasoning into our word problems. And this is going to become the new standard for how you attack word problems. But with these are pretty straightforward. So just copy down the number parts and go through the process and work them out. Okay, so problem 118, do problems A through E. And then I'm not going to go spend too much time with the work that I've shown down here, but I think what I'll do is I'll reveal all of the work, and then you can pause it and you can check your work against my work. I'll be done, but you could just go ahead and make your corrections, okay? Just with the paused video. So go ahead, pause the video now, and when you're ready, I will do the reveal, and then I will show you how I showed my work for every one of these problems. All right, so I'll read this out, then I'll reveal my answer. What is this supposed to be? Tanaya worked 42.2 hours last week, and she makes $15.65 per hour. So what was her total pay? So every hour is $15.65. So that ends up being like a multiplication process, right? So if 1 hour is about $15, 2 would be 30, 10 hours would be 150, 20 hours would be around 300. So 40 hours is going to be somewhere in the 600 range. So that's a multiplication process. So after multiplying those two decimal numbers together, you should have gotten $660.43. And this represents her pay for the week. Okay. Joe has a medicine bottle that has 6 2/3 ounces of liquid medicine in it. Each dose that he's supposed to take is 1/4 ounce. So how many 1/4 ounces can you get out of this bottle? So for my estimating, this seems to me like a division problem, because how many of these can you fit into there? And I know you can fit 4 of these into every ounce. And since there's 6 ounces, I'm thinking your answer's got to be in the 24 to 25 range, right? So after doing the division process with those two, with the mixed number and the fraction, you should have gotten 26 2/3 as your answer. which would mean you'd get 26 full doses from the bottle. And that last 2/3, I don't know what you're doing there with that, but whatever. All right, if the temperature changes negative 2.6 degrees each hour for 8.2 hours, then let's just pretend that's 2 degrees, that it's going down. In 1 hour, it's 2 degrees. In 2 hours, it's going to be 4 degrees. In 8 hours, it's going to be around 16, 17, or 8. So your answer's got to be like in the 17, 18 degrees that it drops in that 8.2 hours. So this is a multiplication process. Okay? You see how I'm modeling my thought process for estimating? You got to read through the problem and make sure you understand what's going on within the problem. If you just look at the problem and look at the numbers and guess at what you're supposed to do with the numbers, you're going to make lots of mistakes. But if you take the time to read the problem and understand what's happening within the problem, you're going to have a lot more success and you'll know what to do. So yeah, it turns out I was really low on my estimate, but yeah, in the negative 21.32, that's how much it dropped. If the temperature dropped 21.32 degrees in that 8.2 hours. Jack and some friends climbed Long's Peak in Rocky Mountain National Park. Then he and his friends started down the mountain, and they lost 1,515 and a quarter feet each hour. All right, so let's round that off to 1,500. In 1 hour, 2 hours would be 3,000, so 4 hours would be 6,000, and 6 hours would be about 9,000. So we're expecting this to be somewhere in the 9,000 range. This looks like a multiplication process. How many total feet of elevation did they lose? They lost 9,394 and 11/20 feet of elevation. The last problem. Mr. Solomon, the art teacher, has 49.6 pounds of clay. If he gives the same amount to every student, 1.6 pounds of clay to each person, how many students must be in the class? So how many of these can you fit into there? This is a division process. So we're going to have to divide decimal numbers. And let's just say this was 2 pounds and that was 50. That means it would be somewhere around 25, right? Because 2 times 25 gets you close to 50. So I expect it to be a little bit more than 25, maybe closer to 30. Let's see what we got here. The answer ends up being exactly 31 students must be in the class. And you know, you can always test this. If you multiply 31 times 1.6, do you get 49.6? If you take this number and divide it by that number, do you get this? If you take this divided by that, do you get this for your answer? So you can always check your numbers. All right, so here's the big reveal. I've shown all the work. If you made some mistakes, look at how I set up the problems. Look at how I did the work. Some of them weren't too much trouble at all. This one, I sort of cheated because I started doing it with the fractions and I realized, oh dear Lord, that's going to be complicated if you keep it in fraction form. So I changed the fractions to decimal numbers, which luckily these are terminating decimals, so it worked. When they're not terminating decimals, like if that was 1/3 instead of 1/4, you'd have to have 0.3 repeated, and that would have been an awful mess. And you would have gotten a rounded off answer, but not the exact one. So it is important to know how to do it with fractions, but sometimes we can do a shortcut and do it with decimals. And not like this was too much of a shortcut, but I found it a little bit easier to do it this way. Okay, so you go ahead. If you need to make your corrections, you pause the video and then just make the changes. And I'm gonna head out, and good luck. And I guess we've got some study guides and a chapter test coming up soon, so hopefully you'll be nice and prepared for that. Take care.
Hey, feeling good, like I should. When in dark,